Hello everybody, this is Antonis Psistakis. Today I'm going to present to you a work that was conducted at ICS 4th in Heraklion, Crete, Greece. The title of this work is PART, which is an acronym for Pinning Avoidance in RDMA Technologies. In this slide, we see the outline of this presentation. First, we're going to describe the background, then we're going to see the contributions of this work, then the environment that we worked on, then we will describe the part mechanism, and then we will see all the results in the evaluation section. And last but not least, we will conclude this presentation. Model computing systems, everything from clusters to heterogeneous accelerator nodes, distributed storage frameworks, key-value stores, data centers, supercomputers, strive to eliminate the use of kernel path in communication. This includes system calls and undesirable memory copies during the transfers that degrade system's performance. Below we see an example where from the source we have a packet from user space that is copied to kernel space, then goes through the sender NIC, then through the receiver NIC, and then from kernel it is copied to the user of the receiver. This of course involves multiple copies. An alternative of that would be user-level initiated RDMA that allows users to bypass the operating system and thus avoids the overheads, which is this case. This mandates the use of virtual addresses for transfers. Regarding the state of the art, common RDMA technologies copy the translation mappings into the network interface cards, which now become responsible to handle the address translations. Planted mappings on TLB-like tables per core are considered to be expensive because they require large tables to fit all of them and also a mechanism that manages them. Lack of page fault support requires all the communication buffers to be pinned in advance in order for the RDMA to have access to them. So here we see an example. We have the source and the destination. Here we have the page table of a process, and the pages are already in memory, pinned, okay, in this example, where the pages are pinned. This is the state of the art, and also the mappings are planted in TLB-like tables here. So a request with a virtual address will be translated from the NIC to a physical address and will have access to the memory. And then in a similar manner, it will go to the destination. But pinning is bad. That is because it hinders the memory utilization, it is incompatible with various operating system optimizations such as the transparency of pages. Pinning and unpinning induces extra system call overheads and increases the programming complexity. Towards the next generation RDMA, in modern well-designed systems, page fault are expected to be a rare phenomenon. That is because buffers are reused. The working sets of HPC applications are dimensioned to fit in memory. Here we have another example. This time the pages are not pinned in memory, and for the translations we use the IMMU that has the mappings of virtual to physical addresses. And it also supports small TLBs and a page table walker in hardware. So at this time, let's assume that at the source the page is already in memory, but at the destination the page is not in memory yet. So the request will go through the IMMU, it will be translated, it will find the page here and will start the transfer. So at the destination, the page is not in memory, so that means that the page fault will be triggered and we need to handle it locally at this node. And upon resolution, an explicit request to retransmit or a timeout will initiate again the retransmission, which will now be successful. So overall, we should say that with this approach that we followed, we can support page faults and we do not need to pin the pages in memory. We should also note that in this paper, we handle page faults similarly to other transmission errors. Now the contributions of this work, PART handles page faults during RDMA by retransmitting the failed pages. This means that no pinning is required. It includes system software and hardware components. We implement PART on a network interface that is closely coupled with the processor, and we also reuse the IMMU for address translation instead of relying on specialized NICs. We evaluate PART in a cluster of interconnected ARM processors, and we present the results from micro-benchmarks and a real HPC application using 16 nodes and 64 cores. Now regarding the environment, we used an RDMA engine, not implemented as part of this work, but implemented from our team. This RDMA engine segments the RDMA transfers into blocks transactions, where each block is 16 kilobytes. For example, a 64 kilobyte transfer is segmented into 4 blocks. Hardware segments blocks further into packets of 256 bytes and selectively retransmits failed blocks. That is, of course, upon a negative acknowledgement or a timeout. The part mechanism, here we will see the general flow. A network memory access goes through the SMMU to be translated. So at this point, it will know if there is a page fault. If there is no page fault, we're done, that's fine. If there is, we need to handle it. We need to bring the pages into the memory. And after that, we have to notify the initiator to retransmit the transfer. That is the flow. Now, getting into more detail, a packet will arrive from the initiator node to the RDMA engine of the target node. The virtual address of this packet will be translated from the SMMU. A page fault will be triggered, and at this point we will have an interrupt and also a negative acknowledgement that will arrive in the RDMA engine. The RDMA engine from its side will notify the initiator node to stop transmitting because there was an error. At this point, we will also push into the network interface FIFO the information that is necessary in order for the page fault handler to later read the information from there and page in the faulty pages. And after that, through the user space, we will send an explicit request to retransmit to the initiator node in order to retransmit the transfer. This time, it will be successful. Now for the evaluation, here we see the information for the testbed. One blade or mezzanine consists of 4 QFDBs, which is an acronym for Quad-FPGA daughter boards. Each QFDB consists of 4 Xilinx UltraScale Plus MP socks. Each MP sock has 4 A53 processors. Each QFDB has 64 GB of DRAM. All components are interconnected with 10 to 17 Gbps high-speed serial links. In total, we used 16 FPGAs with 64 ARM cores. We should also note that in the evaluation, we present only minor page faults. In this figure, we see the RDMA latency where no page fault is exhibited during the RDMA transfer. First, we see the transfer only, where we have no page fault. It is this line, the yellow one. Then we see transfer including the overhead of touching pages that are not present in memory. This means that these pages will exhibit minor MMU page faults. The third line depicts the transfer including the overhead of touching the pages that are already present in memory. So we see here that they have an almost identical pattern, and that is because touching a page that is already in memory costs approximately 200 nanoseconds. In the big color, we see the transfer including the overhead of pinning a buffer. This also involves a minor MMU page fault, and that is why at some point when the transfer size increases, they converge. Now we're going to see the latency breakdown of 4 kilobyte transfers that exhibit a page fault, and to help the audience, we also give here the schematic that we described before. So first, a packet arrives at the receiver and goes to the memory. So first we'll go through the SMMU to be translated. It will exhibit a page fault. This takes approximately 4 microseconds. It will generate an access negative acknowledgement as we saw here, and then we will enqueue in the FIFO the corresponding information. At some point, the page fault handler will be invoked to schedule the tasklet that will page in the necessary pages. This takes approximately 1 microsecond. At some point in time, the tasklet will be run. It will dequeue the information from the FIFO. It will page in the corresponding pages. Then we have a mechanism that notifies the initiator node through user space. This takes approximately 16 microseconds. We should note here that the tasklet involves reading from FIFO and also sending the information to user space through netting sockets. These netting sockets take approximately 10 microseconds. Now at some point, the initiator node will receive the message, and before retrying, this takes approximately 1 microsecond. And the transmission takes approximately 6 microseconds. Overall, this takes about 38 microseconds. In this figure, we evaluate the page fault at destination when all pages exhibit a page fault. Apart from the 4 measures that we've described before, we have 3 more. These 3 involve a page fault during the RDMA transfer. The first one pages in only one page. The second one pages in 4 pages, so it's the first page that exhibited a page fault and the 3 next to it. And the idea behind this is that, as we described before, a block in an RDMA engine consists of 4 pages. So if the first page exhibited a page fault, it is very likely that the next 3 will do the same. We also have here a mechanism that pages in all pages. That means that when a page fault occurs for the first page, we expect that all the pages of the transfer will exhibit a page fault, so we'll try to bring them to memory as well. So this is the blue line, and we see here that performance-wise it dominates all the other 2 page fault, let's say, approaches. In particular, for 1 megabyte transfer, and comparing this to the transfer-only latency that involves no page fault during the RDMA transfer, paging in all pages is 2.6 times worse, while touch no present pages is 2 times worse. These results for 1 megabyte transfer reveal that whether we support page faults and paging in all pages upon a first page fault during the RDMA, or touch or pin the pages prior to the transfer, the latency or the gap for the latency seems to become smaller and smaller. So that means that someone can support page faults and have all the pages exhibit a page fault for the first time, and the next time, because of the reusability of the buffers, there will be no problem. But at the same time, what we gain from that is that we have better memory utilization. Here we see the page fault at destination on a percentage of pages. So with the bars we see the latency, and with the lines we see the slowdown. For this particular figure, we have evaluated only 2 approaches, the page in one page and the page in all pages. Okay, here we see the latency in microseconds, and here the slowdown in times. And the x-axis has the page fault frequency, where 0% means no page fault during the RDMA transfer. So what we notice here is that in all cases from 5% to 100%, paging in all pages is actually better in latency compared to paging one page. Also, when it comes to slowdown, comparing the paging in all pages and transfer only, where we have no page faults, the paging in all pages is 1.15 times worse for up to 5%, 1.56 times for 40%, and 2.6 times for 100%. We also have evaluated a real HPC application called LAMMPS, which involves multiple RDMAs for various transfer sizes. We have used a number of processes that is depicted here, and we have seen 2 measures that actually matter for the LAMMPS, that is the loop time and the time steps. So for the evaluation of LAMMPS, we have 2 approaches. The first one, that is called baseline, involves no page fault during the RDMA, and that is because prior to each RDMA we touch all buffers. So we make sure in a way that no page fault will be exhibited during the RDMA transfer. And in the second case, here we use our mechanism part that exhibits page faults. So what we have noticed is that there is no performance degradation. So to conclude, the part mechanism tolerates occasional page faults, leveraging the retransmission capabilities of the network interface card. It reuses the IMMU and the process page table, so there is no need for separate memory management, and it avoids pinning, and this means that it simplifies the programming model and enjoys the operating system advantages. Now for the performance, there is an overhead of handling page faults during the RDMA transfer, up to 1 times worse for small fraction of pages, up to 5%, and up to 2.6 times for all pages. And we also see no overhead for a real HPC application. Thank you for your time. I'll be happy to take any questions now.